Welcome to this explainer. Today, we're diving into the totally invisible, yet absolutely crucial mechanics that power our everyday digital lives. We're going to look right under the hood of something you probably do, dozens of times a day without even giving it a second thought. I'm talking about how computers manage to find exactly what we're looking for the very split second we ask for it.
I mean, think about this universal problem for just a second. How exactly does your music app find that one specific song out of millions, literally in a fraction of a second? Whether a search engine is hunting down a specific web page or a huge hospital database is pulling up a patient record, or even just your phone finding your mom's contact info, the whole shebang is driven by a search algorithm. And the crazy speed at which we get those results, well, it relies on some really fascinating computational choices.
To really understand search, we actually have to take a step back and look at how we organize data in the first place. So let me introduce you to a real pioneer of algorithm design, Sir Tony Hoare. Back in the late 1950s, while he was at the National Physical Laboratory, he literally taught himself computer programming. Right at the end of that decade, working on a machine translation system for Russian, he invented Quicksort. This is just a brilliantly important algorithm for sorting data. And what's totally wild to me is that Quicksort is still the most widely used general-purpose sorting algorithm in production software today, over 60 years later. No surprise, his work earned him the Turing Award in 1980 and an actual knighthood in the year 2000.
But, despite his absolute genius and all those massive accolades, Sir Tony Hoare is famously humble. He actually joked once that another of his big inventions, the concept of the null reference, was just this unbelievably expensive error. He literally called it his billion-dollar mistake. Because, as you might know, null pointer errors went on to become, hands down, one of the most common and super frustrating sources of software bugs in all of computing history. Just a great little reminder that even the architects of our digital world are, well, human. Anyway, back to his triumph with sorting, because you're going to see why organizing data is so critical in just a minute.
Okay, let's start with the most basic, kind of brute force approach we have, linear search. Essentially, this is exactly like looking for a specific blue shirt in a massive, totally messy pile of laundry on your floor. You just pick up an item, check if it's the blue shirt, and if it's not, toss it aside and check the very next one. The major advantage here is its absolute universality. It imposes zero requirements on the order of your list. The data can be sorted, perfectly reversed, or just totally chaotic. Linear search honestly doesn't care. It just rolls up its sleeves and gets to work.
It's really just sheer sequential effort. We literally start at the first index, compare it to our target, and hey, if it's a match, we're done. We return the index position. But if not, we advance. And we just loop through this until we either find it or we hit the absolute end of the list and return a -1, which basically means, hey, we checked everywhere and it's just not here. You're checking every single item one by one by one.
So, the crucial point you got to take away here is that this reliable old tortoise of an algorithm has a very specific mathematical cost. In the absolute worst-case scenario, meaning the item you want happens to be the very last thing in the list, or maybe it's not even in the list at all, linear search forces you to look at every single element. Computer scientists write this as big O of n. Simply put, the cost grows linearly with the size of the list. Got 10 items? It takes up to 10 checks. If you double that list to 20 items, you literally double your maximum work to 20 checks. It's super predictable, sure, but as lists get huge, it gets painfully slow.
All right, now let's look at the elegant shortcut. Binary search. This is a dramatically faster algorithm, but, and this is a big but, it comes with a super strict condition. It only operates on a sorted list. If linear search is digging through that messy laundry pile, binary search is like finding a specific word in a physical dictionary. You definitely don't start at page 1 and read every single word, right? You open the dictionary right to the middle. If the word you're looking for comes alphabetically before the page you're currently on, you know with absolute 100% certainty that you can completely ignore the entire second half of that huge book. You essentially just rip out the half you don't need and then repeat the exact same process with the remaining pages.
Because the list is already sorted, thanks to organizing algorithms like Tony Hoare's Quicksort, any single element we check neatly divides the remaining list right in two. Is your target smaller than the midpoint? Boom, search the left. Target larger? Search the right. This is an unbelievably powerful mechanism because you aren't just eliminating one wrong answer at a time like we were with linear search. You are literally eliminating half of all possible wrong answers in a single step. Let's just think about this staggering efficiency for a second, okay? Say you have a list of over 1 million sorted items, specifically 1,048,576 elements. Linear search? Yeah, it might have to check over 1 million times if you're unlucky. But binary search, because it slices the list in half every single time, it takes a maximum of just 20 comparisons to either find your target or prove it doesn't exist. 20 checks versus a million. I mean, wow, that right there is the absolute magic of what computer scientists call big O of log base 2 of n.
But theory is just theory. How do these two algorithms actually perform if we put them in a real-world programming lab? Imagine we set up a little test. We generate a sorted list of exactly 1,000 distinct integers. Then we pick totally random targets and run both algorithms just to see how many comparisons they each actually make. It's a classic computer science lab experiment. Let's see what happened.
Okay, so for linear search, finding our target took an average of 500 comparisons, which honestly makes perfect mathematical sense, right? If you're searching sequentially through 1,000 items, on average, you're going to stumble upon what you're looking for right about smack in the middle of the list. So 500 checks on average makes complete sense.
But binary search? It's just completely zipped through that exact same data, finding the target in a blistering average of just 8.9 comparisons. Barely 9 checks compared to 500. It almost feels like a complete magic trick. But no, it's just really brilliant mathematical logic doing its thing.
When actually stack these two approaches head-to-head like this, the trade-offs become incredibly blatantly clear. For linear search, you get ultimate flexibility for totally chaotic data, but it costs you speed. It works perfectly on completely unsorted data, making it awesome for short lists or data you really only ever need to search exactly once. For binary search, you gain massive, exponential speed, making it an absolute necessity for huge databases. But its big Achilles heel is that it strictly, non-negotiably requires sorted data.
And so here is the absolutely crucial point. This incredible speed is not free. Not at all. You cannot just unleash binary search on a totally random pile of data. If your data is unsorted, you literally must pay what we can call the sort tax before you ever get to use binary search. You got to run an algorithm like quicksort first. And get this, sorting data actually takes way more computational effort than just linear searching it. The most efficient sorting algorithms generally have a cost of big O of n log n. It's a pretty heavy upfront investment of computing power.
Which leaves us with the ultimate software engineering trade-off to ponder. Who really pays for that sort, and when is it actually worth the cost? Because look, if you're only going to search a messy list one single time, paying that heavy sort tax just to use binary search, that's actually a complete waste of time. Just use linear search. But if you're building a massive database that's going to be searched millions of times a day, paying that sorting cost once up front saves you millions of computing hours down the line. But here's the thought for you. In a world that is generating literally exabytes of new, unstructured data every single day, sorting it all is rapidly becoming computationally impossible. So, is the future of computing going to be about finding faster ways to sort or completely reinventing how we search in the first place? Definitely something to think about the next time you hit that search button. Thanks for joining me for this explainer.